differences for thin wall and non-thin wall. You can see how the shear flow are designed. But one thing is very interesting is if we were to find at a point A, right? Either you do thin wall or thick wall, the values are the same. Okay. However, at point B, right? At point B, it's different. At point B, this is the area that you take, and this is the thickness. Whereas at point B over here, this is the area that you take, right? And the width is the thickness is what? The width of the box beam. Okay, that's where the difference. So from here, you can see for yourself, right? In thin wall analysis, the shear stress will be higher. Okay, so you can see from here for thin wall analysis. Okay, the shear stress is usually higher. Right? This is because, let's say, if you look at point B, it'll be higher. But at point A, all of them will be the what? Will be the same. Because the area of interest, if it's at point A, right? The area of interest, if it was point A, hold on, at point A, right? The area of interest at point A is this is the area of interest. Together with the shaded region, the area is the same, right? And the area is the same. And the thickness is also the same. Okay, so there's some similarities with the shear, with the values. Okay, but there are also difference. But usually, thin wall analysis, yeah, shearing stress are higher. Now let's look at the thing about thin wall analysis. Designing the shear flow is the most critical thing, and it is not difficult to design. Okay, let me show you some examples. And when you see this example, you say, it ain't that bad. Okay, so let's look at this example over here. Okay, so rule number one, identify, or one of the rules is identify the major what? Major web. Okay, so let's say if now our shear flow is coming down this way, or our Vy is coming down this way. So let's have some transformation. Okay, so this is our X, sorry, our Y, and this is our Z. So we have our Vy. So immediately you know that this is the major web. Okay, the one that I shaded in green. This is the what? The major web. Okay, and we know that Vy, we are interested in IZZ, right? So the axis of interest is ZZ. Okay, so this is a flow, right? So this is one terminal. Then you have another terminal, or you have another flow coming in, and at the bottom is flowing what? Outwards. Okay. So now this down here has how many terminal? We have terminal 1, terminal 2, terminal 3, terminal 4, terminal 5, terminal 6. Okay. So now, why designing the terminal is so critical? Okay, and I'm now going to show you why. Okay. If we want to find, looking at the flow, okay, if we want to find the shear stress or the shear stress at A by looking at the terminal, right? So this is our terminal 1. At A, you only consider this area over here. At point B, relative to the terminal, okay, relative to the terminal. So the terminal 2, okay, or I call it terminal 3, right? So the arrow, you know that it's flowing this way, right? So this is the area. And then you ask me, Eugene, how about C? To consider C, you have to take this entire area over here. Because all the flow, okay, all the flow will go into C. Okay, so the formula to use is still the same. Shear stress is equal to VQ over IT. Constant, this one, the thickness is, for this case, everything seems to be like, okay, for this case, it depends, it can be 12 or 10 millimeters. This is the one that's always causing the what? The problem. Okay, so at C, you take the top head section, okay? And this is visualized through the what? Through the shear flow. Are we clear? Okay, this is visualized through the shear flow. Okay, let's do another one. Okay, let's do another one. Now, what if now, right? What if now is different, right? So what if now we have VZ? Okay, so rather than Vy now we're going to start from what? VZ. Okay, VZ. So now if we were to look at VZ, how does the shear flow flow? Okay, so where are our major web now? This now are our what? Major web. Can you all see that? Okay, so these are now our what? Our major web. Okay, this is also our major web. So your Q will now flow this way. Okay, now the centroid now, okay, now if I'm going to draw the centroid, this is our Vy, we have to use what? Iyy. I'm sorry, Vz, we have to use Iyy, right? So in case some of you forget, right? What do I mean by that? The shear stress, okay, let me draw in a different color. The shear stress can be equal to Vy over Izz Qz over T. Or the shear stress can be Bz over Iyy Qy over what? T. Right? So Vz over Iyy, right? So now, the shear flow now for this case, okay, because it's at the centroid, you can flow away this direction. Okay. So what we see now is how many terminals we have? We have 1, 2, 3, 4, 5, 6, and over here 7. But I have something to tell you. Okay. Mathematically, and it's a fact. Okay. At this part over here, not that part. Wait. At this part over here, I'm going to use a different. I'm going to use a thicker. Okay. Now this section over here, everything over here, right? The shear stress are equal to 0. Okay, the shear stress are equal to 0. Okay. Why? Can someone tell me why? Why is the shear stress equal to 0 if it's Vz? You can type or you can talk to me. I hope I can hear you. Anyone? Okay, I'll tell you. Okay. So we know that Qy is equal to width, depth, Z bar. Okay. Okay. So this is our width. This is our what? Depth. So the width is equal to 50. The depth is equal to what? Is equal to 12. The Z bar is equal to what? 0. So this is equal to 0. So anything, you can see now, right? Mathematically, okay? Sometimes you have to just trust the math. I know it's some, especially when I started knowing this topic, I find it real confusing also. Only the math can prove it to you. Are we clear? Okay, so we know that this section over here that I'm highlighting in orange, they don't carry any what? Shear stress. All mathematically is shown. Are we clear? Okay, mathematically shown. Okay, so you can do whatever now. Okay, you can do multiple loading condition, whatever, you'll be fine. Okay. Now the next thing I want to show. Anyone, any questions so far? Are you okay? This I think this is the fun part of this of this what do you call of this thin wall analysis. Okay, you just need to apply all the rules that I've taught you. It's not that difficult at all. Okay, let's do another one. Yeah, let's do another one. Let's do with this one. Okay, we're gonna do two directions. Okay, we're gonna do two directions. Okay, so we again, this is our x, no, our y, our z, and what we have now is we have by. So the first thing you have to identify where is your major web. I repeat again, you have to firstly identify where's your major web, and the major web have to be continuous from the top to bottom, and this seems to be continuous from the top and bottom. The left and right one are not, because you have what? It's broken. Okay. So how does the shear flow? So we know that we are going to focus on the axis is ZZ axis. All right. So the shear flow will go this way. And then we'll split up. Okay. And then we'll split up again. Okay. And then this one will do this. And then this one will do this. So terminal 1, terminal 2, terminal 3, terminal 4. Now this point over here, where it's split, this is known as a junction. It's not a terminal. This is also known as a what? Junction. It is not a terminal at all. Are we clear? Okay. It is known as our junction, and it's not our terminal. Okay. I'm checking. Someone put up their hand. Oh no, no one. Okay, it's recording. Yep. Okay. Okay, now let's look at what if we have our forces, okay?